Well, hi and welcome. I'd like to talk to you today about some introduction to statistics. So I'm going to cover types of data you might have, data distributions. You might have heard of things like normal distribution, so I'll be talking about types of data distribution, hypothesis testing, significant levels, parametric and non-parametric statistics. There's different types. Tests for normality, which might sound a bit interesting. Tests for homogeneity of variance, and then we'll go through some examples. We'll look at the student's t-test, and we'll look at one-way ANOVA, and post hoc testing, which is associated with the ANOVA. So there's different types of data. So if you think about some properties such as height, mass, percentage change, these are all what's known as scale properties, or interval, might be called ratio data. So these have a varying sort of continuous number. And there's another type of data called nominal data. This is categorical data, so it might be groups like blood groups, countries, rivers, yes no answers. So something where there's some kind of grouping effect. So it's not a continuous number, but there are definite groups. And then there's something called ordinal data. This is a bit like groups, but there's some kind of ranking. So it might be something like salary range. I'm sure you've all filled in application forms, etc., where you have to put down what salary range you envisage or you're on at the moment perhaps, and so you'll be ticking a box to say you're in this value here, 1 to 9999, or 10,000 to 19,999, etc. So there's some kind of order to the categories. Likert scales, I'm sure you've all done questionnaires where you write down things like very much agree, agree, neither agree or disagree, then disagree, and very much disagree. So that would be an example of a Likert scale as well. So it's like nominal data. I mean, there are groups, categories, but there's some kind of order to it. So that's what's called ordinal data. Data can be distributed. So if I was to look at the heights of people in a room, for example, there would be some tall people, some shorter people, and there would be some kind of average in between. And the data would, for heights of people in a room, it will probably be, if you had the big enough room and looked at measured enough people, you would find this type of shape curve. It's called a bell shape curve sometimes, or otherwise known as a normal distribution. IQ might be another one as well. So IQ has been specially arranged so that the average IQ is 100, and people with above average IQ have IQs above 100. So people with IQs below 100 would be lower than that, and it would follow this type of distribution in a population of people. Something else I need to define here, standard deviation. Okay, so this is the variation from the mean, and it's given this equation here. So x with a bar on the top means mean, and xi is all the individual data values. So in order to get the standard deviation, you work it out using this equation here. So you have each individual data item minus the mean, and then you square that term, and then it's the sum of all those differences squared. So you work out the difference, square it, then it's the sum of all those, and you divide by n minus 1, where n is the number of data items. And then you do the square root of the whole thing, and that's what's known as the standard deviation. And with a normal distribution, if you look at the top left graph there, you have mu, which is sometimes used for mean, so that's also x bar, and you have your mean in the middle of the distribution. And then if the data's normal distribution, you have 34.1% of your data between the mean and the first standard deviation, and another 34.1% of the data between the mean and the standard deviation below the mean. And similarly, you have another 13.6% of the data 2 standard deviations away. So from the first standard deviation to the second standard deviation, and also on the other side of the graph between the first standard deviation and the second standard deviation. And you can also go up to the third standard deviation. And by that point, you've captured most of the data. So you're getting up to close to 100% within 3 standard deviations, just a little bit outside. Of course, you may get data which is skewed in some way. Okay, so it might be that your population maybe has more taller people than average, and so your data might have a negative skew, like you see on the graph down the bottom there, or it might have a positive skew. Maybe some in your population you're sampling, there's shorter people than average, or it might be any other property, of course. So you see these skews in the data. So hypothesis testing is where you set out to test whether there's a statistical difference between 2 groups in terms of their property. So the example I said about people's height in a room, maybe you've got 2 different rooms. It's a strange example, but maybe you've got 2 different rooms, and you want to compare the heights of people in those 2 different rooms, and you want to see, is there a statistical difference? So this is what's known as hypothesis testing. So you set out what's known as a null hypothesis, given this symbol H0, and this is, you say there is no statistical difference between these 2 groups. And then there's an alternative hypothesis called H1, and this is where you say there is a statistical difference between the heights of people in the 2 different groups, 2 different rooms. And so what you would set about doing is to prove whether the null hypothesis, if you have to accept that, or whether you can reject the null hypothesis and go for the alternative hypothesis where there is a statistical difference. And in hypothesis testing there are 2 different types of testing. One is a one-tailed hypothesis, and this looks at whether there is a difference between distributions only in one direction. So your H1, which is your alternative hypothesis, might be that the heights of members in group A are taller than members in group B. That would be a one-tailed hypothesis. So you're only looking at the difference whether they are taller. Whereas a 2-tailed hypothesis would be looking at, is there a difference in the heights of people in the room in both directions? So are some shorter or taller? So rather than just looking at the whether they're taller, and then you say there is a difference, you're looking at the shorter and the taller. So there's loads of different examples where you would go for one-tailed or 2-tailed. Another factor to consider is the alpha value. This is what's known as the significance level. The alpha value is a preset value to which the calculated p-value is compared. So it's also known as the probability of rejecting H0 when H0 is true. So usually the significance level chosen is 95%, or an alpha is 0.05. If the p-value is less or equal to alpha, then you reject h0. In other words, there is a statistical difference between the two groups. If p is greater than alpha, then you can't reject h0, and there is no significant difference between the two groups. So the value of 0.05 is usually chosen if you want a tighter control, then you can set it to, say, 99% significance level, and in which case alpha will be 0.01. But what normally happens is you use the alpha as 0.05. There's another term what you need to be familiar with, and that's called parametric and non-parametric statistics. So with parametric statistics, these are the most robust, in other words, the most reliable tests, and you are comparing means. So for an example, you might have come across the term a student's t-test, and this is for testing to see if there's a statistical difference between two groups. So n is 2, n being the number of groups. If you've got more than two groups, you need to use an ANOVA, which is called the analysis of variance. So you can see analysis of variance, that's where ANOVA comes from. And so this is when n is greater than 2. So you've got 3 groups. So for example, if you're looking at the heights of people in a room, and so if you had 2 groups, then you use a t-test. If you had 3 groups, you wanted to see is there a difference between group 1 and group 2, or group 2 and group 3, or group 1 and group 3. They are the 3 comparisons you would need to make for n equals 3. Then you would carry out an ANOVA, and ANOVA would tell you that there is a statistical difference between at least 2 of the groups, but it won't tell you where that difference lies. In order to find that out, you need to do what's known as a post hoc test. So it might be you carry out the post hoc test and you see, oh, there's difference between groups 3 and 2, but there isn't a difference, say, between 1 and 3 and what was the other one? so there's a difference between 2 and 3, but there isn't one between 1 and 2 and 1 and 3. Yeah, so that's the sort of thing you would do. So using an ANOVA, that says yes, there's a difference. If there is a difference, then you go on to do the post hoc testing. If there isn't a difference, then you just stop there and you say there's no statistical difference between any of the group comparisons. So that's the ANOVA. But the thing is, you can only use parametric statistics if the data are independent, they are normally distributed, and they have homogeneity of variance. And quite often in research papers, etc., you see parametric statistics being used, in other words, a t-test or an ANOVA, when the data is clearly not normally distributed. In other words, if they haven't done enough samples, so there's no way the data can be normally distributed, or perhaps there's no homogeneity of variance there, so that hasn't been tested and it's not obvious in the paper. So what do we mean by independence? Well, independence data means that so if you go back to the people in the group, height of people in the room example, you're not counting the same data twice. So in that case, it's quite simple. You wouldn't have one person being measured in one room and then running through to the other group and then being measured again. Yeah, so they're 2 separate groups. Normally distributed, well, we've seen our bell-shaped curve, and the data must look like that in order to proceed with the parametric statistics. And homogeneity of variance we haven't discussed yet, but we'll discuss that very shortly. So all these 3 conditions have got to be met before you can go ahead with parametric statistics. If it fails those tests on normality, and if the data has not got homogeneity or variance, which we'll talk about shortly, then a way to proceed is non-parametric statistics. And these are less robust, in other words, they're less reliable tests, and they rely on comparing rank values of data. So the parametric statistics compares means, and the non-parametric statistics compares rank values. So examples of this are the Mann-Whitney U-test, which is the non-parametric version of the t-test. So again, comparing two groups, n equals 2. Or the Kruskal-Wallis test, which is a non-parametric version of the ANOVA. So everything I said about the ANOVA, n's greater than 2, but say it fails the normality test, then Kruskal-Wallis test might be the way to go. So you can use that when data is not normally distributed, or you have a heterogeneity of variance. But data must be independent, though. For the non-parametric and the parametric statistics, the data must be independent. So let's have a look at some real data. So this example, we've got two histograms there on the top left and bottom left, and you have a distribution which looks like it might be normally distributed, but you can see there's some variations within that profile which might make you think, is it normally distributed or is it not? Well, and just judging it by eye, is that good enough? Well, what we can do here is we can do a statistical test. In SPSS, we can do what's known as a Shapiro-Wilk test. And this, when you run this, you run it on each distribution. So we can run it on the distribution on the top one and on the bottom one. And we have a value of, if you look at the circled area, 0.811 for group 1. And then for the group 2 we have a value of 0.204. So these are p-values, and we can see that the p-value is greater than our alpha value of 0.05. So we can say there's no significant difference. So no significant difference meaning no deviation from what you'd expect from a normal distribution. Okay, so we're not doing the t-test now. We're not comparing the distributions to each other. All we're doing is looking at the distribution and seeing if it has a deviation from our normal distribution. And so we have our p-value is greater than 0.05, so we can say there's no significant difference from normality, therefore it's normally distributed. SPSS also provides what's known as a QQ plot, and I won't really go into this at the moment, but you can read up about it. I'll put some links up. But if you've got a straight line plot, a linear QQ plot, that means it's normally distributed. But again, when you look at these plots, sometimes there's a deviation even on that plot, which makes you think, well, I'm not quite sure whether it's normally distributed or not. So the safest way is to do this Shapiro-Wilk test, which you've got this cutoff at 0.05, and that gives you a definitive answer. Even if your normality plots look a little bit a bit wonky in places, you can just look at the Shapiro-Wilk test and it will give you your p-value, and you can instantly say whether it's normally distributed or not. So in this next section, let's look at what we mean by homogeneity of variance. Well, variance is standard deviation squared, and it's a measure of the spread in data. So the value is around a mean, the spread of data. So that's our equation for standard deviation, as we saw previously, and the standard deviation squared is our variance. And if we had a variance of 0, that would mean that all the values are identical, which will probably never happen. You'll normally have this distribution. But if you have a high variance, a high value of the let's give them this symbol, sigma. If sigma squared rather is the variance, sigma is the standard deviation. So if you had a high sigma squared, high variance, this will mean you have a high spread of data around the central mean. So it's spread away from the central mean. So you have a wide distribution. If you have a low variance, it means it's a tighter distribution. It's more closer to the mean, and it would spread out less. So for parametric statistics, equal variances of groups being compared are required. So you must have an equal variance in the group distributions in order to be able to proceed with parametric statistics. And having this equal distribution is what's known as having homogeneity of variance. If you don't have that homogeneity of variance, it's called heterogeneity of variance, and you would need to proceed via a non-parametric method. Okay, so you need, remember, for parametric statistics you need data to be independent, you need it to be normally distributed, and then the third thing is you need homogeneity of variance. So homogeneity of variance means that the spread of data between the two groups is considered equal. So you might have some data like this. We're comparing, say, males and females with some property, and both data might have a mean of 6, but you can see there's a variance on both. So the variance might be 5.87 for males, and the variance in some property might be 5.62 for females. And then you might think, well, okay, that variance looks similar. Is it statistically similar, or is there some difference? And there's a test for doing that as well. It's called the Levene's test, also known as the F test, and this is commonly used to test for homogeneity of variance. So let's have a look at some examples. Say you have a student obtained a sand sample from a beach, say South Sea Beach in Portsmouth, and another sample from say Brighton Beach, not too far away, and you wanted to compare the grain sizes of these sand grains. So some might be coarser, some might be finer. Is there a significant difference between the grain size between these two samples? So these two groups, you could say. So we could set up a null hypothesis, H0, and this would be that the sand particles from the two beaches are the same. And we could also set up a alternative hypothesis, H1. The sand particles from the two beaches are different. And we say different, in other words, it could be smaller in Portsmouth or larger in Portsmouth, so it would be a two-tailed. We could set up a one-tailed if we wanted to say that the coarse, the sand particles on Brighton Beach are coarser than those on Portsmouth Beach. That would be a one-tailed. So let's have a two-tailed. We're just seeing if there's a difference. We don't care whether it's which way around it is. The sample data is clearly independent, unless we accidentally mix the samples up. We assume that's not the case. So we need to do a normality test, and then we need to do a test for homogeneity of variance. And so the test we would use for this is a student's t-test. If it passes the normality test, and if it passes the homogeneity, a variance test, then we will proceed with a student's t-test, because n equals 2. And n is the group number, nothing to do with how many grains are in that sample. So it's just the group number. So here is some data you might use. So we got group 1 and group 2. And then the first thing is to do the Shapiro-Wilk test to check for normality. And we can see that both these p-values, 0.539 for grain for group 1, that might be the Portsmouth group, and the Brighton group, say 0.682. So both these values are greater than 0.05, which is our alpha value. So therefore we can say that the data is normally distributed. Okay, so then we can proceed to the homogeneity of variance test, which is called the Levene's test. And here we can see that the significance value here, 0.506. And this tells you that it's greater than 0.05, which is our alpha value again. So we've got homogeneity of variance. Okay, so our spread of data from the particles on Southsea Beach and Brighton Beach are the same. Therefore we can proceed with the student's t-test. So the significance value here, 0.848. So p is greater than 0.05. That means there's no significant difference between the two means, and therefore we cannot reject the null hypothesis. In other words, that the grain sizes on Southsea Beach and Brighton Beach are the same. Say we want to do a comparison between grains of sand on 5 different beaches, maybe beaches across the world, maybe some exotic places. So we've got 5 distributions. So we set up the null hypothesis that the sand particles from all the beaches are the same. Our alternative hypothesis, H1, will be that sand particles from at least 2 of the beaches are different. By difference, what I'm looking at is an H1, so the sand particles, maybe it's the diameter or the radius or something like that, from at least 2 of the beaches are different. So this is our two-tailed test, and we look for a difference. Are there any differences between at least 2 of the beaches? Remember, the ANOVA only tells you if there's a difference between at least one of the pairs. So we got 5 here. So we got 5. So we got quite a few comparisons. We got 1 and 2, 1 and 3, 1 and 4, 1 and 5, then 1 and 3, 1 and 4. No, I said that one. 2 and 3, 2 and 4, 2 and 5, 3 and 4, and I think any other combinations, no, 4 and 5 also. Any other combinations there, I'm repeating myself. So 1 and 2 is obviously the same as 2 and 1. You get the idea. So again, we assume the sample data is independent. In other words, we're not mixing any of our samples. Grains from one batch of samples isn't being contaminated into another group of samples. And the next thing is to detect for normality, like we've done before, and heterogeneity as well, like we've done before. And then the test to use, therefore, assuming it passes those tests, assuming the data in all those groups is normally distributed and there's homogeneity, and if there's a similar spread in all those groups, then you can proceed to the ANOVA. If it fails one of those tests, then you'd have to do the non-parametric version, and so you would use a Kruskal-Wallis, which is a non-parametric version of the ANOVA. So this is some examples what you might obtain. So we got our 5 different samples, and then we do the Shapiro-Wilk test to work out the p-value, which tells you whether it's normally distributed or not. So in all those distributions, p is greater than 0.05, so therefore all the data is normally distributed, regardless of really what the histogram looks like. Although you can, obviously, I would advise you to look at the histograms, to have a look at the data, but then you rely on the Shapiro-Wilk test, which says whether it's normally distributed or not. Again, you can do the QQ plots to see if they're linear, but I would rely on the Shapiro-Wilk test. Then you do the Levene's test, which tests for homogeneity of variance. So in this case, our p-value comes out at 0.825, which is greater than 0.05. So therefore, there is homogeneity of variance. So in this case, you're looking for a p-value which is greater than 0.05. That means you can proceed with the ANOVA, because remember, if p is greater than 0.05 in the Levene's test, that means you've got homogeneity of variance, therefore you can proceed with the parametric statistics. So then you do the ANOVA itself, and you get a value of 0.000. Now with the ANOVA in SPSS, quite often it just gives you this p-value to 3 decimal places, and if you've got 0.000, it doesn't mean 0, it means the third decimal place is less than 1. So, but if you double click on with the software, if you double click on that 0.000, it will give you what the actual value of the p is. So it might give you a value, say 1 times 10 to the minus 6, a very small number, for example. But the important thing is the p is less than 0.05, which is our alpha value. So this means there is a significant difference between at least one pair of means. So you can reject the null hypothesis. You don't know which pair is giving that difference. It might be from sample 3 and 5, or it might be all the samples, or just some of them. So what you then do is a post hoc analysis test, and this is what this looks like. It looks a bit complicated, but all you're really comparing is on the left hand side there, sample 1 against 2, so sample 1 against 2, sample 1 against 3, sample 1 against 4, sample 1 against 5, and then you're looking at the significance level, which is the second red circle, and here you're looking at the p, if p is greater than 0.05. If it is greater, there's no significant difference. If it's less than or equal to, then there is a significant difference. And again, where it's 0.000, you can double click on that and get the actual p-value itself. So you can see there are some differences and there's not some differences. And you've got also the comparison between 2 and 1, 3, 4, 5, and then 3 and 1, 2, 3, 4, 5. So you've got these different comparisons on this left hand side. Now some of them will be the same, like I say. Between 1 and 2 is the same as between 2 and 1. But as you go down, there will be some differences which don't appear in the other boxes. So say 3 and 4, you haven't compared elsewhere. I suppose you compared it between 4 and 3. So half of this table is been replicated. But you can just go through, see where those significant values are, and that will tell you where the significance lies.